Hi, my name is Fareed Shreve from Glen Ellen, Virginia, and my research is about traffic management, specifically an algorithm that uses machine learning and graph theory to predict traffic on road networks and better inform traffic intersection control. Traffic management is a complex subject with centuries of history behind it, originating in a single human-managed traffic intersection. But as land vehicles proliferated and traffic intersections became mainstays, traffic management grew from being managed by humans to being simulated and controlled by machines, which themselves grew from small devices with very limited memory and calculation ability to the behemoths with sensors snaking under roads they are today. But nearly all traffic management algorithms and systems today rely on a single overarching assumption. These systems attempt to collect all the data they can in real time and use that data to manage traffic in the present. In other words, they assume that the most efficient way to optimize traffic is through real-time traffic optimization. But that assumption may not necessarily be the most sound. You see, I'm a chess player, and in chess, you often have to think multiple moves ahead to get an advantage. An advantage you usually would not be able to get by thinking only a single move ahead. Figures 1 and 2 show the results of thinking one move ahead versus thinking multiple. In figure 1, white actually ends up either in a losing or drawn position when trying to think one move ahead and gaining a single pawn. In contrast, figure 2 shows what happens when you think multiple moves ahead, and white is now in a winning position and is set to gain not only the pawn, but the rook as well. I considered current real-time traffic algorithms to be like novice chess players, only thinking one move ahead, and formulated a revised assumption about traffic management systems. The most efficient optimization comes not from optimizing the present in real time, but in optimizing using both present and future data, optimizing across time. Figure 3 shows the results of this new assumption, right here. While a traffic algorithm that only relies on real-time data would attempt to alleviate traffic flow in the north road, a traffic algorithm that can forecast traffic in the near future would see that the south road is actually due for significantly more traffic than any other traffic intersection and would therefore alleviate south road traffic, thus leading to more optimal traffic management. Now, while this assumption may seem reasonable at first, it can only be supported through scientific validation. After designing LMOPP, or Edge Load Management and Optimization through pseudoflow prediction, which used nested long short-term memory modules, or NLSTM for short, a machine learning architecture built to learn from and predict sequential data like traffic flow in a road, I compared my algorithm to two other traffic management algorithms in silico. In other words, I used a simulation to compare the throughput rate, a measure of traffic flow over an intersection, where the greater the rate, the better traffic is optimized across all three algorithms as seen in figures 8 and 9, over a 4-star graph, which is shown in figure 9, which models a 4-lane traffic intersection. I then conducted t-tests across all pairs of algorithms and found that the calculated t-values far exceeded the t-table values for every single test, meaning that the difference between the throughput rate of each algorithm was very significant. My research supports the claim that the LMOPP algorithm maintains a higher throughput rate than the other two algorithms against which it was tested, the ITLC and OAF algorithms, while using far less resources. Though the ITLC and OAF algorithms use wireless transceivers, GPS systems, and vehicle traffic light communication systems to facilitate information collection and traffic management, the LMOPP algorithm only needs access to traffic cameras, from which it processes various traffic-related data. Because of how few resources it needs compared to other traffic management algorithms, LMOPP would not only be an effective traffic management system, but would be relatively easy to install and would both be more portable than and to cost less than other algorithms. Something with immediately obvious implications for poor regions of the world that require traffic management, not to mention the decrease in vehicular pollution caused by increased traffic flow. In contrast to previous traffic management algorithms, which focus on real-time traffic optimization, the LMOPP algorithm attempts to optimize traffic across time by searching for the most efficient traffic flow using machine-learned traffic patterns to predict future traffic. But although my algorithm was built for traffic optimization, by dint of it being based in graph theory, LMOPP could actually be applied to various other fields that rely on network optimization, from internet networks to economic networks or even human traffic to enforce social distancing, an especially pressing issue in today's pandemic.